Hello, today we will be explaining what a rheostat is, how it's constructed, how it works, and finally, its different applications. If you have a basic understanding of electronics, you would already know that a resistor opposes the flow of current in an electrical circuit. A rheostat is also a resistor, but its resistance can be varied to control the flow of current in a circuit. Therefore, we also call it a variable resistor. With a rheostat, there's no need to connect separate resistors for increasing or decreasing the equivalent resistance, since it can perform both functions. Now let's get to the construction and working of a rheostat. Note that this is a linear rheostat. Rheostats have two connection points. One is moving and the other one is fixed. Similar to a potentiometer, some rheostats can have three connection points, A, B, and C, as shown in Figure 1. But still, only two of them are used. Here, points A and C are fixed points, and point B is the moving point. Rheostats are made up of wire-wound resistors to bear large currents. They may also be called variable wire-wound resistors. They're mainly constructed by wrapping nichrome wire across a ceramic core. Such a core behaves as an insulator to the heat energy and does not permit it to flow through the rheostat. Okay, moving toward its working principles. Now let's assume that we are first using the fixed point A and the moving point B of the rheostat illustrated in Figure 1. The rheostat will offer minimum resistance to the circuit if you move the slider close to point A, since the resistive coil's length is at a minimum, and a large current can flow through the circuit in this case. Similarly, the rheostat will offer maximum resistance if you move the slider close to point C, as the resistive coil length is at its maximum, and a tiny amount of current would flow through the circuit. Now let's look at the second case where we use the fixed point C and the moving point B. In this case, when you move the slider close to point C, the rheostat would offer minimum resistance and maximum current flow through the circuit. Likewise, when the slider is moved closer to point A, the rheostat would offer maximum resistance and minimum current flow through the circuit. So that's how a linear rheostat works. Now, we'll move on to another type of rheostat called a rotary rheostat, which is very similar to a potentiometer. This type of rheostat particularly comes in handy when there is a need to get a full-scale variation using one full turn. A rotary rheostat has three terminals, a rotary resistive path, and a slider mounted on the shaft, as shown in the figure. Similar to a linear rheostat, only two of its three terminals are used. One terminal is attached to the slider, and the other one is attached to the resistive path. You'll need to rotate the slider over the resistive path to increase or decrease its resistance. The resistance will change because of the change in length of the resistive path. This, in turn, will change the voltage level across it. One example of an application for a rotary rheostat would be to alter the speed of electric motors by changing their armature voltages. It's worth noting that rheostats have maximum and minimum resistance ratings, and thus they cannot offer resistance outside their inherited range. Okay, now let's quickly go through the applications of rheostats. You can use them in situations where high voltage is needed. They're frequently used in light dimmers. When the rheostat resistance changes, the electric current through the bulb changes, which then changes the light intensity. They're also commonly used in radios to increase or decrease volume. Also, they're often used to control electric motor speed. Lastly, rheostats can be used in heaters or ovens to control temperature. Okay, so that was all for today. Stay tuned for more interesting videos on electronics. If you have any questions, you can ask in the comments below. Please like our video and subscribe to our channel if you found this video interesting or helpful. Learn, shop, save. All things electronic at derf.com.